Okay, so now we'll introduce instantaneous velocity, which is going to be measured at a single point now instead of over an interval of time, like the average velocity was. Okay, so suppose you've got a particular point in time, and that is what this t star is going to represent. Okay, but just to be clear, t is still going to be the name of the variable that represents time, but t star is going to be a particular value of t, or in other words, it's going to be a particular point in time. Right? And then v of t star is actually going to be the notation that represents the instantaneous velocity of this object that's traveling in one dimension. Okay, so let's fill that in, the instantaneous velocity. Okay, and what is it defined to be? Well, here's the idea. Take your position graph, which we've got a position graph sketched right here, and then sketch the tangent line at the point t s of t star. And that's what this point is here that I'm drawing the tangent line at. Right, because if the t coordinate is t star, then the y coordinate is going to be what you get if you plug t star into this function. So the y coordinate is going to be s of t star. So that's why this really is the point t star s of t star. So start by looking at the tangent line at that point, and really v of t star is going to be its slope. So that's the definition. Okay. The instantaneous velocity at the point t star is going to be the slope of the tangent line to the position graph at the point t star s of t star, which is this point right here. Okay, but that raises a fairly difficult problem. We need a method for computing these slopes, right? We can't compute the slope of this tangent line using the typical formula for slope because that would require 2 points, right? We only have 1 point that's on this line. Okay, so here's what we're going to do. We're going to approximate the slope of this line by taking the average velocity over an interval which contains t star. Right? And the idea is that the width of this interval that we use, which is really what this h variable is for, can be whatever we want. So you can take h to be absolutely any positive number you want. You can form the corresponding interval t star to t star plus h, and then you can compute the average velocity of this underlying object over that interval. And well, what do you get if you calculate the average velocity over this interval? Well, you get the following. I'm going to write v of t star is approximately equal to, and then I'm going to write down what you would get if you apply the average velocity formula to this interval. Okay, so if you do it carefully, you're going to get s of t star plus h minus s of t star all divided by h. Why is that? Well, look at the previous page. Remember the definition of average velocity over a time interval t0 to t1 was given by this fraction? Your t0 is t star, and your t1 is t star plus h. So if you plug t star plus h in here and t star here, then you get t star plus h minus t star. You're just going to be left with h down at the bottom. So that's why this is the actual approximation that you get. So a question you might ask, rightly ask, is this approximation going to be any good? Because it might feel like we're admitting defeat. If we're at the point now where we have to resort to approximations, that might almost sound like we are giving up on the idea of finding a way to actually compute the instantaneous velocity directly, but that's actually not the case. But the first thing we need to do is answer the question of, is this approximation going to be good or not? And the answer is, well, it depends on how large this value h was that you chose, right? The quality of this approximation is going to depend on how big or how small h is. Let's look at a couple of examples in these pictures below. Okay, so I've got the same picture twice, and in both cases I've got a t star and a t star plus h labeled on the t-axis. But you can see in the second picture the t star plus h is closer. So let's just start by sketching the tangent line in both pictures. It's going to look something like this. Here's the tangent line in the first picture, and in the second picture it's going to look like this. Same line, of course. Alright, well, what do we get if we take the average velocity over the interval t star to t star plus h in the first picture? Well, I'm going to draw this one in green just so it stands out, but really, remember the average velocity is really just the slope of the secant line. So you're talking about the slope of this green line that I'm sketching now, where the instantaneous velocity is the slope of the blue line. Let's just remind ourselves that. Okay, so v of t star is the slope of that line. And the slope of this green line is given by, well, s of t star plus h minus s of t star, all divided by h. Okay, so is that approximation good if we use this as an approximation for v of t star? Well, probably not, actually. It doesn't look like it's that good of an approximation. Now, you could certainly do a lot worse, but I would not say that that's a very good approximation. And really what it comes down to is what we have here, this value of h is quite large. So this approximation is poor. In other words, it's not very good. And the reason is, since h, our positive number h, is large. All right, well, what about in the second picture? Let's draw a sketch of the secant line that we would use to define the average velocity over t star to t star plus h in the second picture. So the secant line is going to look like this. And, oops, I didn't mean to turn that at an angle. You could ask the question, well, is that a good approximation? Well, again, it might be subjective. Somebody might look at that and think it's a great approximation, and somebody else might look at it and say it's not a very good approximation. But one thing is for sure, it's certainly better than this approximation, right? Let's fill the labels in for this picture just for practice to remind ourselves what everything is. So the slope of the tangent line is your instantaneous velocity v of t star. This may seem repetitive, but it's good practice. Give yourself a chance to absorb these ideas. And then the slope of the secant line is given by the approximation s of t star plus h minus s of t star all over h. So that's the slope of the green line. Okay, and this one, we had our h value, which was just the distance between those two endpoints. This approximation is better because h is small. And now just remind ourselves that h is a positive number. In this case, is small. Okay, and notice I used the word better because I didn't want to go as far as to say that this approximation is actually good, because that's a subjective thing to say. But one thing we can definitely say objectively is that this approximation for the instantaneous velocity is better than this approximation. Is better than this approximation for the instantaneous velocity. Okay, so finally you should ask yourself the following question. What would happen if you drew another picture with an even smaller value of h, and you took an approximation of the instantaneous velocity using the slope of the secant line, or in other words, the average velocity over this time interval? What if you did it again, but for a smaller value of h? And then you could ask yourself the same question again. What happens if you did it again with even another value of h that was smaller still? And what would happen if you just kept doing this over and over and over again with smaller and smaller and smaller values of h, and you just kept doing this till the end of time? Well, the answer is, what would happen is that your approximations would get closer and closer and closer to the exact instantaneous velocity. And this is what we're going to use to come up with a formula for instantaneous velocity. So I'm going to write it down here. This is what we write. V of t star is equal to, and notice I'm writing an equals sign here, unlike above at this line where I wrote an approximately equal to sign, right? Because this was just an approximation. It's not actually a formula for the instantaneous velocity. But this down here is actually going to be a formula. So here's how you can calculate the instantaneous velocity. You take the limit as h goes to 0. Now this notation is the first time I've introduced this, but this is really what we're going to spend all of chapter 2 dealing with coming up with a good understanding of what this notation means. So it's okay if this doesn't make perfect sense right now. I haven't told you everything. But the instantaneous velocity v of t star, it's going to be the limit as h goes to 0 of exactly this approximation formula. So we're going to write s of t star plus h minus s of t star all divided by h. Okay, so let me add one more comment before we go on to the next page. I want to really zero in on this notation. This means what happens as h gets arbitrarily close to 0. Okay, and geometrically, what you should imagine that this notation, what it really does, it's like a vacuum cleaner at t star. It just takes the t star plus h point, it just sucks it in towards t star, it pulls it in, right? Like you're vacuuming up some dust. And that would have the same effect as taking this point up here and pulling it in really tight and close to this point. And just imagine what would happen to the green line if you did that. It would become indistinguishable from the blue line. So the slope of the green line, which is down here, would become indistinguishable from the slope of the tangent line. That's the idea. Okay, but if we can come up with a good definition for what this notation means, if we can make it do what I just claimed it did, then we'd be in business and we would have the slope of the tangent line. So that's the technique, and this is the formula that we use.